Okay, thank you for this introduction and for inviting me to deliver a talk. I really feel honored to be a part of this lecture series. And probably my internet is showing little problem. That is why the video is, I cannot see my video. But still, since the presentation is okay, I think you can see my slides.
Yes, yes.
Okay, so let me start. Yes. The topic that I'm going to give a talk on numerical solutions of ordinary differential equations. And this is one of the important topic of our mathematical field. Let me start with a quote by Heraclitus, that is, the only constant in life is change. Everything is changing, whether it is the location where you are sitting right now or any other physical properties are changing at every moment with time. So everything is changing. So we are interested on the change, and more importantly, instead of the change, we are interested in rate of change. So whenever the concept of rate of change come up, then the concept of differential and or the differential equations comes in. Introduction. Many mathematical laws of physics or chemistry can be formulated as differential equations. In engineering or life sciences, and even in social sciences, differential equations are used to model behavior of complex systems. In particular, the origin of differential equations may be considered as the effort of Newton to illustrate the motion of particles. In many real-world processes, the variables representing the process and their rate of change are related to each other in terms of some basic principles of the process. The basic definition, though all of you know all about the differential equation, a differential equation is a relation between independent variables, dependent variables, and its first or higher order derivatives. For example, here we have considered a simple differential equation f of xy dy dx. So this is a first order general form of equation, differential equation. Now the classification of differential equation, that is a very important, the concept is very important in the process of solution. First of all, we need to classify the equation. Now depending on the number of independent variables, we may classify the differential equations.
ये जो ब्लैक पेन जो मैंने लेके आया था, तो उसमें क्या पॉकेट इतना टाइट हो रहा है, हाथ घुसने में प्रॉब्लम हो रहा है.
Am I audible?
हाँ, जो ब्लैक पेन एक पॉकेट में हाथ घुसने में टाइट हो रहा है.
Hello, am I audible? Please, anyone may confirm.
Yes, sir.
Okay, okay. Thank you. So this classification, depending on the number of independent variables, differential equations may be categorized as ordinary differential equation and partial differential equation. When the number of independent variable is 1, then an equation is termed as ordinary, otherwise it is partial. Again, the next important criteria for classification is the linearity. Depending on the linearity of the independent variables, a differential equation may be classified as linear and nonlinear differential equations. Now, some popular ordinary differential equations. Since this topic is about solution of ordinary differential equations, so I have just included few popularly known ordinary differential equations we are all familiar with from school level only. Also, we have seen these equations. Now, popular growth model is first order first degree linear differential equation when alpha is greater than 0. If alpha is less than 0, then that will be decaying model. For example, this one, law of radioactive decay, is the same equation you can observe, but here k is less than 0, or the constant of proportionality is less than 0 or negative. A simple harmonic motion, we are familiar with this equation, ordinary second order equation. Newton's second law of motion, that is force is rate of change of momentum, a differential equation. Newton's law of cooling is another differential equation of first order, first degree ordinary differential equations. So there are so many equations of this type of first order differential equation or higher order differential equations, ordinary differential equation obviously. Now the general solution of any differential equation contains arbitrary constants that is equal to the number of order of the equations. That is also known as the general solution is also known as complete primitive or the complete integral. Now, solutions obtained from general solution by giving particular values to the arbitrary constants is called particular solution. Now, different methods that available to solve a differential equation are analytical method, iterative method or successive approximations, then series solution method, transformation methods using integral transformation, then solving by software packages, and finally the numerical methods. Now, analytical method is the method where we have started with from +2 level, or this is by manipulating the terms we can find the solution analytically or logically step by step. In the iterative method, we have say Picard's iterative methods. Series solution, we have Taylor series method, Taylor series solution method, and then transformation methods using integral transformation like Laplace transform, Fourier transform, wavelet transformation, then Henkel transformation. There are so many transformation techniques are available to solve differential equations. And also nowadays there are packages, software packages that can solve a certain category of differential equations, so using software packages. And then finally the numerical methods. Now, why I have said this is finally, now when a differential equation is solvable by analytical approach, that is the solution of the differential equation. But when we adopt a iterative method or series method or any transformation method, most of the time the solution may not exact, and if it may give some approximate solution. Integral transformation method may give exact solution, but not always. It may not be possible. So when all this method fails to solve a differential equation, then we need to adopt the numerical method. That is only way out for us. Now, if a solution, considering the solution of a differential equation, the general solution may be possible, but what about the particular solution? A particular solution of a differential equation may or may not exist. So based on certain theorem, we can justify, or we can be sure that whether a differential equation may have an unique solution or it does not. So if we consider a simple differential equation, this is the first order first degree ordinary differential equation, and if a condition is given to us And then this condition along with this equation is known as initial value problem. So if this P, PET and GT are continuous in a particular interval, say I, containing this point T naught is a continuous in this particular interval, then this problem has a initial value problem has a solution, unique solution. Now this is the linear equation, and this is the more general form, the last equation, the general form of the first order, first degree ordinary differential equation. And because of this initial condition, we call this as initial value problem. Now if this f, that is the f and del f del y are continuous in some rectangle alpha to beta and gamma to delta, this t from alpha to beta in an interval this one, and y from gamma to delta in a rectangle. So if these two functions f and del f del y are continuous in some rectangle containing a point t naught y naught, here t naught is this one and y naught is this one, the initial value of the dependent variable, are continuous, then in some neighborhood of t naught we have the unique solution of the differential equation this one, and the solution let us term it by this, that y is equal to phi t is the solution of the initial value problem this. Once we are sure, we are little bit certain that the solution is unique, then we can approach for the solution of the equation. Now why numerical method? As just I have mentioned, though a solution of a differential equation may exist, but it is not always possible to find the solution phi t by symbolic manipulations of the differential equation. Nevertheless, it's a fact that solutions of vast majority of first order IVP, that is initial value problem, cannot be found by analytical approach, and that is why the importance of the importance of the numerical method. So today there are numerous methods that produce numerical approximations to the solutions of differential equations. An Euler method, that is also known as tangent line method, is the oldest and the simplest of such numerical methods, originated by Leonhard Euler in about 1768. So this is the oldest method, is Euler's method, and also the simplest one. Let us discuss a little bit about this equation and the process of solution by the Euler's method. So let us consider this initial value problem, general form of first order first degree ordinary differential equation along with this initial condition, and let us assume that conditions for the existence and uniqueness is satisfies. Then there exists a unique solution y is equal to phi t of the given problem 1 in some interval about t is equal to t naught. So once we are sure that the solution exists, then you can approach for the solution of this IVP1. Now this is the geometrical interpretation, how the solution can be obtained by this method. So this is the t-axis and this is the y-axis. Here at a point t is equal to, at a point t in t naught, the value of y naught is given to us. From equation number 1, at t is equal to t naught, the value of y naught is y naught of y is given to us. In other words, this point is known to us. This point is known to us. Also, from the equation 1, this function f of ty is nothing but dy dt. So this is a slope. This represents a slope, and this is a known function, and we know the value of t naught and y naught. So substituting value of t naught and y naught here, this function f is also known to us. F of f at t naught y naught. So the slope at this particular point is also known to us. So this point is known to us, and the slope at this point is also known to us. So once we know the point and the slope, then we can draw the line. There is a tangent line at this tangent line to this curve at this particular point. So the tangent line is given by the equation number 2. Now what is this tangent line about? This tangent line about is the tangent line of the actual solution curve. Here at this moment we do not know the solution curve. Since we do not know the solution curve, but we know the tangent at this point of the solution curve, And that is why we will take a nearer point, say T1. T1 is a point which is very close to T0. In the diagram, you can see they are very at a large distance, but that is for display purpose only. But it is to be understood that this T0 is a point very close to T0, and hence this particular point T1, wherever it intersected this one, then this is the solution. This is the value of y, the dependent variable. But this is the actual solution curve. Though we do not know the exact solution curve, but let us assume this is the exact solution curve. But the solution we have obtained at this particular point. So this is nothing but the error. This difference is the error. Now, since we have obtained this particular equation number 2, that is the tangent line, so putting t is equal to t1 here, putting t is equal to t1 at this point, we have the value of the dependent variable, and let us call it as y1. So we have called this as, this length is y1. So now, coming to this particular point, this point is known to us, since we have taken this t0 by ourselves, and the calculated y1 is known to us. So this point is known to us. And once we know the value of t1 and t1 and y1, then the function f at t1, y1 is also known to us. So at this particular point, we know the point and also know the slope at this point. So we also draw another tangent line at this particular point. So this process will be continued. This process will be continued to get the next value close to t1. In this process, in this way, we'll continue to get a desired value of t. And by this process, now this process may be continued to generate a sequence of values. That is y1, y2, y3, etc. that approximate the values of the solution phi t at the points t1, t2, t3. So these solutions y1, y2, y3, whatever solutions we get at the points t1, t2, t3, these are all approximated solutions by the process of this tangent line method. Now the general solution or the general expression for y of n plus 1, y at n plus 1 is given by this equation number 6. It is y n plus 1 equals to yn, f of t and yn, and t of n minus n plus 1 minus tn. So this is the n plus 1th value, and phi at t n plus 1. So since in the previous stage we know the value of tn, yn is known, suppose, then tn is known because it is according to our assumption, yn is known, this is we choose, so this is known to us. So all this in the right hand side are known to us, and that is why yn plus is also. Now if we mark f of t and yn by this symbol, and we consider all of this tn plus 1 minus tn is a constant value, h, this is equals to tn plus 1 is equals to tn plus h, that is we take the t values at equal intervals, then we have this equation number 6 can be put in this particular form. It is y n plus 1 at n plus 1 yn plus h into f of n. So this is the Euler's method to solve the IVP 1. Now by this method, if we solve a differential equation, this is the differential equation that we have solved, and this is the initial condition. And this equation can also be solved analytically. So these are the exact solution for this equation. And solution at different in step size. This is known as step size. H is equals to 0.1 is 0.05, 0.025, and 0.0. So decreasing value of h. So you can see these are the exact solution, means this is the value of the dependent variable. And these are approximated solutions based on the particular method and taking the different step size. Now observe the last row. At t is equal to 5.0, the exact value is 5.7403. When we take h is equal to 0.1, so this is 5.7707. We can observe closely that the result that by this method we obtain is correct up to the first decimal place. Then the first digit after the decimal point. But when we decrease the value of h, we have seen, so this result is also correct up to first decimal place, but this result is more better than that of this result. And that is because we have decreased the value of h from 0.1 to 0.5. Again, we further decreasing the value of h, we have seen this particular result or this particular result are correct up to the second decimal place. And when we further decrease, this is correct up to the second decimal place, but this is better approximated result than that of this one when we compare this particular value. Another example. So when we compare now, these are different values of h. These are differential equation. We have showed this by Euler's method, and these are the exact solutions. So observe the last row. This is the exact value, 3540 and then 0.2001. But when you take h is equal to 0.5, the result is 1745. The error by this method or taking h is equal to 0.5 is very large. It is unacceptable error that we have obtained by taking h is equal to 0.5. So further decreasing the value of h, we have seen that this result is improving because this is 3540. So from taking h is equal to 0.05, at t is equal to 2.0, that from 1745, it is improving to 4732. Still, the error is very high. Now, further decreasing the value of h, we have seen it is 3029, closing to exact value, but still error is not tolerable. Further decreasing the value of h, we have seen that there is still the error exists, but the error is much more smaller when you take a large value of h. So by this trend of this both the problem, we have seen that while decreasing the value of h, the in Euler method, the solution or approximated solution may be improved or error may be reduced. Now, for the use of numerical procedure to solve an initial value problem of the type 1, one need to address the following. First, whether the solution converges. Only getting solution is not sufficient. Only getting one step, two step is not sufficient. We should be sure that the solution converges. That is, with decreasing value of h. Decreasing value of h, do the values of the numerical solution, these are the approximated solution, approach the corresponding values of the actual solution, whether this satisfies or not. Secondly, if the solution converges, we need to address how rapidly the numerical approximation converges. In other words, how small a step size is needed to guarantee a given level of accuracy. So the solution is not only sufficient, we must try to address its error. First of all, whether it converges or not, and then how much error a particular method gives. Then step size should be small enough to assure the required accuracy, but not too small. Because sometimes in decreasing the value of h may create some other type of error. That is mostly the round off error. Now there are two fundamental sources of error. These are truncation error and round off error. If we assume our computer is such that we can carry out all computations with complete accuracy, we can retain infinite number of decimal places. If we assume, then the difference En between the solution, exact solution, and numerical approximation is given by this quantity, and it is known as truncation error, global truncation error. Our computer, we know, say 1/3. 1/3, if we put in terms of decimal in floating point, then we'll have to put it 0.3333, etc. So this is, we have to truncate somewhere. So our computer cannot give us the exact result for this type of value, say 1/3. There are so many values of this type. So if we assume that our computer gives the exact value, still, and if this En is the this Yn is the expected result, that is by the Euler's method, yn that what we have calculated, that is the expected calculated value, and the exact value. This difference is known as the global truncation error. But this is not the only error. One more error is there, that is due to the round off error, because our computer cannot calculate infinite number of digits. Now this global truncation error arises due to at each step we use approximate formula to determine yn plus 1, and the input data at each steps are only approximately correct, since in general phi of Tn is not equal to y. Now let me go back to the formula once again. Why this much of error we have seen? Let me go back to this equation 2 once again. Here at this stage we have shown that this is the error. This is the error if we take this is T1. If we take this is equal to T1, then we have y1 is this much, and this much is the error that is at the first stage, that is at y1, this much is the error that what we have seen. But in the next stage, that is while in order to finding the value of y2, we will have similar error. I'm repeating, in the process of finding the value of y2, we will have similar error. In addition to that, while finding the value of y2, we have taken a particular value of y1 is this one. This is the exact value of y1, but what value we have taken is this one. So there are two types of error. One is at each step we are accumulating error, and in each step, since previous data is also containing some error, and that is why the next result will also enhance its error. Okay, so this is the global truncation error, and the reason I have already described. Now round off error is another kind of error, and that also depend on that. Now there are the process of finding rounding error is very much complicated. Different algorithm uses different process to find round off error. Finally, I'm not going to go in detail about round off error, but finally this is the exact value at Tn, and this is our calculated value. Exact value minus calculated value. So this difference is the total error, and total error is bounded by the global truncation error and the round off error. So in order to get our result more correct or to reduce error, we need to concentrate on both the errors. Now local truncation error for Euler's method. Euler's method, if we see that this is the exact value and this is the expected computed value, and the difference is we denote it by small en. This is the local truncation error, and its value to determine the error by a particular method. Okay, so the local truncation error for Euler's method is of order H2, if order H2, and the global truncation error, this one. Now how to select the step size? Just I have mentioned in those two particular tables that while decreasing the value of H, it may possible for us to reduce error and to get more accurate results. But the question comes, how to choose the value of a suitable value of H? Suitable value of H may be chosen from this particular concept. That is, from this one, if we take capital M be the maximum value of this one, capital M be the maximum value of this one, then En plus 1 at nth stage, or say En at nth stage is m into h square by 2. This is from this particular term. Or this equation can be 11 can be rewritten in the form of 12. This equation 11 can be rewritten in the form of 12. This one. If we take out epsilon be the tolerance error. Let me read out. If, for example, the local truncation error must be not greater than epsilon, this is the error of tolerance, then for the above equation, we have h is less than or equal to under root 2 epsilon divided by m. So how to choose m or suitable value of h, how to choose a suitable value of h, that can be determined from this particular formulation. Again, the finding the value of m is not so easy. That is another topic. I'm not going to go in details about that. Now, again, more important than the local truncation error is the global truncation error. That is finally what the result we obtained, that is the exact error or final error, and that is why we are interested about when we get the final result, and that all the error accumulated during till the end, that is known as the global truncation error. And the global truncation error for this Euler's method is proportional to the h. H is the step size. That is, our error depends on the value of h directly. And since the error of Euler's method is proportional to step size h, and that is why this Euler's method is known as the first order method. And that is why we have seen by this method the error is very much high. Now, improved Euler method. Since we have seen by Euler method, the error for a can understand this yn, approximated yn, or the value of phi at tn, and f of tn plus 1, that is the next points. Let me discuss this particular diagram. Here tn and tn plus 1 are two neighboring points, or there is the gap of tn and tn plus 1 is h. H may be equal to 0.1 or 0.0001. So this is the gap of tn and t plus 1. Now, in the Euler's method, what we did, we took the tangent at this particular point and took the solution that was touching at this particular curve or tangent line point. But in this improved Euler method, what we do, first of all, from this initial point, if it is a t naught, from initial point, we obtain the value of t1, y1, t1, y1, and then at t1, y1, we again draw another tangent. And now from these 2 points, we take the average of the slopes that is reflected by this formula. There is slope at tn point and slope at tn plus 1 and yn plus 1. The average of this one divided by 2. So we take the slope in this way. So if we take the average of these two slope in order to take yn plus 1, we have obtained the equation number 14, and that is the improvement of the Euler's method. What is this equation 14 about? Yn plus 1 is equals to yn like Euler's method, but in Euler's method we had h into fn, but here h by 2, that is the average of the slope at fn was there in Euler's method. Here fn and then f of tn plus h, that is tn plus 1, and yn plus h into this. What is this about? This is from this is nothing but yn plus 1 from the Euler's method. Please recall Euler method. Euler's method, yn plus 1 is equals to yn plus h into fn. So here again we are using Euler's method to take the average of the two slopes, that is at fn and f of n plus 1 in that sense we can say. So this is a two-stage method because we first calculate the value of this one, that is this one, or the value of f once. F. Again we have to calculate the value of f at another point. So we are calculating the value of f at n, and we are again calculating the value of f at n plus 1. And that is why this particular method is termed as two-stage method. Also, the local truncation error by using the equation number 5, that is this one, is proportional to h cube, whereas the global truncation error is proportional to h square by the improved method. And that is why this method is known as second order method. This is order of h is 2, and that is why it is second order method. This greater accuracy, that is from h2, from Euler's method, it was about proportional to h, and in this method is proportional to h square. This greater accuracy is achieved at the expense of more computational work, since it is now necessary to evaluate fti twice in order to get the value of tn to tn plus 1. Just now I have mentioned, while in the process of this one, we have to calculate this one once and this one another time. So this is, we are giving, or we are computing more twice, and that is why we are correcting our result or reducing our error. So now let us compare this particular table. In this particular table, we have shown here the Euler's method and the improved Euler's method. Here, a tabulated value. Let us concentrate on the very last line, that is at t is equal to 0.2 or 2.0. T is equal to 2.0, and this is the exact value. The previous problem only, the table 2 itself, we have extended table 2 here. Now this is the exact value, and by Euler's method, when you take h is equal to 0.001, this is the result. And this result is not equal to this one, and there is an error. But when we use the improved Euler method, at h is equal to 0.01, this particular result is more accurate than that of this result. You can observe it is 3484 and it is 3532, and the exact result is 3540. So this result is much more accurate than that of this result. But if you see the value of h here, we have taken at 0.001, but here we have taken h is equal to 0.1. So from this h to h, from this particular point, we need to compute 10 times. That is, when we multiply 10 times to the h, we have h is equal to 0.001. So improved Euler method, when you take lesser or increased or greater value of h, our results are more correct in comparison to the Euler's method. So this is the improvement of the Euler's method. And this result we have mentioned already, that this accuracy we have obtained because we are computing f just double than that what we used in case of Euler's method. Now Tangakuta method, this method uses a weighted average of the slopes on a given interval tn to tn plus 1. That is, in improved Euler method, what we have seen, that it took, or the improved Euler method takes average at the slope at tn and at tn plus 1. But in Tangakuta method, we take weighted average. That is, if we take only two slopes at Tangakuta method, this will reduce to the improved Euler method only. But here, Tangakuta method actually it's a series of methods. We can take 3 slopes in between tn or tn plus 1, including the endpoints. We can take 4 slopes, 5 slopes, 6 slopes, etc. So this is more widely used. That classical fourth order Tangakuta method is given by this one. This is 1 by 6 into h. Here we'll discuss this one. This is 2 2. So 1 plus 2 plus 2 plus 1. So all this accumulate equal to 6, and that is why it is 1 by 6. And this is K1, Kn1 at nth stage is f of Tn Yn. Kn2 is equals to f of Tn h by 2 Yn h by 2 into this. So this is another slope at this particular point. This is slope at another point. Slope at another point. This is the end point. These are two. This is at Tn. This is at Tn plus 1. This one, and these are two intermediate points in between this one. So we, in Tangakuta fourth order method, we have taken 4 slopes and taken the average of all those slopes. Now we can also understand by this, in this particular Tangakuta method, we need to calculate here f once. This is f once, twice, 3 times, and 4 times. So we have to calculate for, in order to get the value of yn plus 1 from yn, we have to calculate f 4 times. And that is why this method is also known as fourth stage method. Now the local truncation error in using classical Tangakuta method is 4, is h to the power 5. Local truncation error, that is truncation error at each stage, will have h to the power 5. So if we take h is equal to 0.1, then the local truncation error in Euler method is proportional to 0.1. But here in this case, it will be 0.00001. And the global truncation error is proportional to h to the power 4. And so this Tangakuta method is known as fourth order Tangakuta method. So fourth stage Tangakuta method is fourth order Tangakuta method because its global truncation error is h power 4. So this particular method gives us more correct results than comparison to the other discussed results. So this is another table. Okay. So we have used the same problem or same table we have extended, and now we have compared with the, this method with the improved Euler method. In improved Euler method, if we take h is equal to 0.25, then we have this particular results. And when we take h is equal to 0.1 in Tangakuta method, and you can see this particular result is much more correct than that of this one when we compare with the abstract value. When h is 0.1 but h is 0.025 in Euler method. And when you take h is equal to 0.05 in Tangakuta method, then we have this result 3539, and the exact result is 3540.2. So this is how we have improved the original result by using Euler's method to the Tangakuta fourth order method. And here h we have taken is 0.05 only. This is much more greater than that of this one. Now this result can also be improved by taking more by taking averages of more slopes at each stages. But in that sense also our computations expense will go on increase. But if we can accept this is our result, then it's okay. Also, in order to improve this particular result, we can also decrease the value of h. Say h is equal to 0.01. If we take h is equal to 0.01, we have not shown in the diagram, then obviously in that sense our result will become more correct. With this, let me conclude. So within time, I think I have finished. So any query from your side? this particular presentation is especially meant to the students. Basically, when I talked with a couple, yes, he has even students will be there, basically MSc and PhD students. So I guess if any students have any query regarding this particular topic, then they may share. Yes, sir. Yes, sir. Okay. Is this okay? Okay. Yes. Yes. Is it diverging or it is converging? You are talking about a particular value of t that is equal to 5.0, is it? Okay, okay. Let me explain once again. Here, at t is equal to 5.0, the exact solution is 5.74. But when we take h is equal to 0.1, it is 5.77. So, if we yeah, if we calculate the error will be approximately 0.03, right? Error will be approximately 0.03. But when we decrease the value of h, say 0.05, the calculated error will be 0.01. No, no, no. It is, see, after the decimal point, it is 7707 and it is 7555. Is it clear? It is 77, it is 75. So it is decreasing. The error is decreasing. Yes, further again the error is decreasing. It is 5747. It is 755 and it is 747. Again, in the next stage, when it further decreased, it is 0.743. It was 747, it was 743. So again the error is decreasing. Okay, okay. Yes, yes. Yes, 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 yes. Yeah. Since I was little fast because of time constraint and so it's okay. Same thing. Thank you so much, and thank you for inviting me, all of you.
Thank you, Ashish,
Thank
accepting
you
this
very much.
invitation.
I'm also, feel honored to deliver this talk.
Thank you very much.
Okay. Thank you so much. You're welcome. Okay. Let me sign out.